chairman of this session, power and energy. This session we have five papers. First paper consists of solar cell battery charger with DC isolate forward converter at signal technique of linear controller design. This paper will be presented by Pacharavit from Pacharavit. He's obtained the bachelor degree in power electronics from College of Industrial Technology, Kimmungkut University of Technology, North Bangkok. Now currently he is the
Good morning. My name is Washirit Parung Sachis, and assist Professor Dr. Anusak Bisram and Professor Nordin Chakobet and Professor Pajipat Tuantong. I am from Kimmungkut University for Technology, North Bangkok. Today we will present about analysis of solar cell battery charger with DC to DC isolate forward resonant reset converter with large signal model technique for linear controller design. We are going to cover 5 areas today. Let's begin with our first point. Today, pollution tends to increase and cause an effect on human and life. That is problem. So many countries are interested in alternative energy and renewable energy to decrease using for conventional energy. Solar energy is one for renewable energy, which is widely used in the world, especially in the particular country, but an electric power generation for solar cell depends on the sunlight each day that could the variation for the amount of power and power consumption. To resolve that limitation, generated solar power is stored in the battery, which voltage and current must be optimized for that battery. And to optimize voltage and current for battery, PI controller design naturally with the design of controller require an analysis of the converter. So we will present design of PI controller for mechanical model of forward resonant reset converter using evaluating large signal model method. Analysis of proposed circuit. For the elemental, we analyze this circuit that's called DC to DC isolate forward resonant reset converter FRCR based on solar cell battery charger. For input side and output side, we use value of parameter following this slide to analyze in KVL and KCL for all three states and find VCR, ILM, ILX, and VCO. The first stage occurrence when switch M1 works at time T0 to T1. That's called the electric current flow for electric supply to a reset capacitor to the high frequency magnetizing inductor and high frequency transformer expectedly. So the voltage VCR would be equal to VP, and we got variable relationship of the current flowing to the high frequency magnetizing inductor following this slide. At the beginning of this state, the power switch MOSFET is turned off at time magnetizing inductor LM, release the energy and commutation energy reset flux saturation between ILM and reset capacitor CR on the high frequency transformer at the moment T1 to T2 and waveform reset approximate is 2/3 of the half period switching time GS and can be seen suicidal waveform. So we got KVL and KCL on input side and output side. At the time when its capacitance CR as constrained full energy received fallback of current magnetizing inductor From last time G1 to G2 are during complete time are the old. D1 and D2 turn on remain current. Continue add to all complement output DC side. To consider relation differential equation in the T state. Equation state 1, state 2, state 3, and state 3. Where rewrite in the state space form evaluate form to find match model. 1, 2, and 3 state. Combine parameter and vector system matrix in the red box. To find the output matrix, we sum sub inputs B1, B2, and B3 from C state. And system matrix and input matrix can be derive relationship state variable. Simulation match model open loop resolve. We simulation match model of derived relationship of state variable by using simulating program. The purpose of mechanical model simulation is to verify that the method was correctly analyzed and to study dynamic state and the state variable of system. Firstly, as number one is output voltage and next one is output current. In the third is VCR and finally the in fourth is the ILM. Design of control unit. The linear PI control was applied in controller design to controller. The output voltage to be constant is maintained. The current for battery charging to design this controller voltage and current loop is necessary. The controller design is using frequency response technique focused on cut-off frequency. From solution solving, we got equation for Kp and Ki. To find Ki and Kp, we could frequency from both diagram and phase angle for a transfer function in each voltage and current loop. For one state loop control, the system cut-off frequency is minus 19 dB and the phase angle is minus 81 degree at 145 Hz of frequency. And for the current loop, the system cut-off frequency design at 2.98 dB and the phase angle is minus 78.7 degree at 22 kHz. Kp and Ki of voltage and current loop shown in slide. This slide presents the load transform no load to critical load condition. There are three simple states. We are going to talk about 100 to 50%, 0 to 50%, and 0 to 100% of the load. The transition from full load condition to half load condition cost 11.28 millisecond with 14.67 volt of overshoot and 12.29 millisecond with 14.13 volt of undershoot. Transition from half load condition to no load condition cost 11.57 millisecond with 14.67 volt of overshoot and 12.92 millisecond with 14.13 volt of overshoot. The transition from no load condition to full load condition cost 3.14 millisecond with 14.93 volt of overshoot and 50.18 millisecond with 13.87 volt of overshoot. This slide presents ethanol resource total dynamic response of the attentive undershoot and recovery time while charging T condition load from no load to half load and from half load to no load based on return load. The first constant was 5 millisecond to set point. The current load is right from no load to full load in the secondary condition. Usually speaking, point of 8 millisecond. Minor attention from half load to full load at 5 millisecond. To set point was made in the third compute state when the alternative set point value is used. The condition understood by around 4%. This is a prototype of proposed skit. Conclusion. The simulation result verified that the design parameter can be used maintain a constant voltage at 14.4 volt. Overall, goods under and undershoot and percent regulation response in each experiment. In the experimental result closed loop control, there are conditions undershoot by around 4%. An alternative set point value is employed the efficiency of the system was measured and value was 93% at full and maximum efficiency about 96%. The suggested analysis approach and mechanical model by averaging large signal model method was validated by simulation. Result is good dynamic result that concur with the theory analysis. Thank you.
Thank you very much for your presentation. In order to decide the further set the goal by the PI controller, what is the goal?
The goal design is the set constant voltage output in a charge battery charger. For a battery charger, it output voltage 14.4 and maximum current at 2 ampere.
If you apply this,
Yeah.
so
Okay. In very 9 volts to 15 volts, vary in input voltage. Okay.
you still have a lot of time. Just a simple question also. Do you mean, in your paper topic, what you decide, right? Based.
Oh, okay. That is in design rationale technique เนี่ย for easy to design the to controller
Usually, you obtain and control function. But I don't understand that drag signal technique. Use drag signal, we think about circuit or big drop of voltage. Thank you much
Thank you.
presentation. Let me skip to second paper. This is study of performance of flexible power control with empirical lithium-ion battery modeling in PV power system. This paper will be present by Mr. Acharavat Chindamani, Department of Electrical Engineering, Kasetsat University. Is currently.
Thank you, Mr. Chairman. Hello, ladies and gentlemen. My name is Pacharavat Chindamani from Kasetsat University, Thailand. Today, I would like to present the research topic study on performance of flexible power control with empirical lithium-ion battery in PV power systems. Is the outline of this research can be divided into 4 parts: production, methodology, simulation result, and conclusion. First, introduction. One of the most promising resources for large-scale power generation is PV power generation. The capacity of power energy produced by solar cell from 2010 to 2020 is increasing every year. Large number of grid-connected PV installation needs to meet the power quality requirements. The main problem of PV power generation depend on weather condition. Right-hand side, this graph show the relation between solar radiance and time. And as you can see, the high fluctuation occur in the day. From this high fluctuation of PV power, also much high power RAM rate as shown in this figure. And this power RAM rate can be calculated from delta P over delta T. And we want to control the high power RAM rate under the limit we explained in the next slide. To control high power RAM rate, we propose flexible power point tracking or FPPT with battery energy storage or BESS. This graph on the blue line, is the PV power without FPPT. So the RAM rate is over 10%. And on the green line is the PV power without FPPT, with FPPT and BESS. So the RAM rate control under the limit at 10% for the both RAM up and RAM down. And this research used this circuit configuration to verify the proposed effect of flexible power control on batteries performance with non-linear parameters. Consists of PV panels, boost converter, and boost converter with dual mode operation. And dual mode operation consists of 2 main parts: maximum power point tracking or MPT and power RAM rate control or PRRC. And the bidirectional converter with RAM rate limitation, battery management system, and the inverter. In this research, focusing on the BESS to understand the performance of PV of battery characteristic to PV system operation. We are expand the model of battery. For this BESS model, we use transient response model for the BESS on the right-hand side. Model of a single cell of lithium manganese oxide. And this structure perform well in fast charge and discharge operation, has a large current capability, and has low internal resistance. And on the right-hand side, the battery modeling for the equivalent circuit, and this model include 4 nonlinear components. One, open circuit voltage. 2, effective series resistance. 3, the first R1C1 parallel circuit. And for the second R2C2 parallel circuit. Then this can lead to understanding the battery behavior, especially the characteristic changes of effect effective series resistance because operation is greatly influenced by the chemical process inside the battery. On the transient response model of battery, we will apply the transient response model to each cell of the battery. So the actual battery model comes like this. The battery packs connect series, and each battery pack has T parallel cells and I series box. After designing a wall battery cells, total battery rating is 63 volt and battery capacity is 650 watt hour. Control algorithm for the calculate RAM rate. To calculate RAM rate, we use this equation. After we have RAM rate value. In case of RAM rate is higher than the limit, the controller operates in PRRC RAM up mode. Of course, there is a critical before a sudden drop in solar radiation. That case, the converter will operate in PRRC RAM down mode before the. If RAM rate or if RAM down exceed the limit, the FPGA operate with BESS in discharge mode. On the other hand, BESS operate in charging mode, and MPPT mode works in normal operation. In this research, hardware in the loop is used for simulation, and we use simulate at 3 kilowatt PV system and use high-full hardware in the loop. And we set parameter RAM rate limit is 5 watt per second, and measurement sampling period 2.5 seconds, and FPV sampling period 0.1 second. And this table parameter for the battery cell. FPV operation with BESS figure 1 and 2 show the PV power generation profile on February 2022 from 11 a.m. to 12 p.m. The PV actual radiant profile for the is supply at the input to proceed PV system. Comparison of FPV operation with BESS and operation without FPV is conducive to better understand the battery's response to the FPV. And in this figure G and 4 show that require BESS rating with FPV is 500 watt, which is smaller than without FPV is 800 watt. At a result, our RAM rate in the system can be controlled under the limit at 10% by FPT, and battery unit can supply partial power to the system. Finally, the conclusion. The hardware in the loop simulation result of the PV power generation verify the proposed control method of FPT and BESS with 4 nonlinear parameters for the both ramp up and ramp down events. BES with 4 nonlinear parameter model can visualize the actual operation, the FPD control. And this is a good guide us for battery lifetime determination and degradation in EV system in the future. Thank you for your attention.
Thank you very much for interesting presentation.
Actually,
Right now,
in the battery lifetime in the future for the future work, they are temporary. Wow.
first idea is
Actually, the battery with power RAM rate in the PV system. Sorry for the
anyway,
future.
I understand. Yeah. But I think this depend on the setting of study. You can and value. Once you know depth of power, but as from my understanding, talk about the model.
Battery cells.
Battery.
These 4 parameters, right?
Yeah.
These 4 parameters get from the laboratory battery testing because I follow this parameter from this paper or laboratory battery test. And actually the limitation of Typhoon hardware in the loop program, why we design the 650 watt hour because that program Typhoon hardware in the loop because the program resource are limited and this will affect the real time and this parameter rating for the simulation at the program. And we calculate RAM rate at 10% for the support the RAM rate RAM down during the variable period on the February 2022 from the 11 a.m. on the 11 a.m. to 12 p.m.
Question? Thank you very much for your presentation. Try to move to the first paper. This investigation of effect of solar photovoltaic penetration in an ideal low heater system. Paper issue Stanley, he's a researcher at AISSMS IOTT College of Engineering. Yeah. Worked as a senior engineer at Maharashtra State Electricity Distribution Company, which is second largest power distribution company. And he worked as a general manager, Gujarat Energy Department.
Topic is investigation of effects of solar voltaic in IEEE 13 bus radial low voltage distribution feeder system. Some of us know that solar and energy helping us to reduce the emissions. To highlight as is taking making use of the solar PV. But in India, we have got statistical figure. Power generation is 395.6 gigawatts. 10% of energy which is being generated in India. About the generation of same time waste have the excessive penetration of power generated by SP result into the current voltage distribution factor, power balancing for low voltage distribution. So in our work, what we have done is that we have studied or simulated all these parameters in the MATLAB Simulink analysis. We have used the Newton-Raphson method for the load flow analysis. And the important thing which we have presented in this paper is the effect of SPV penetration on voltage rise, power factor, voltage harmonics, and current harmonics. And what we are trying to conclude is that the permissible SPU penetration level is determined from the observations. So with this, I would request my author, Mr. Shinde, to proceed with the implementation part. Thank you.
Brief information regarding the research work and the effects which we are trying to study on the different parameters which are arising because of the integration or the increase in the integration of SPV studied within this and submitted in this paper. To explain in detail, I have just taken a small SLD of a distribution system, which is a radial distribution system, where I'm trying to indicate some nodes. V0 is the traditional node, or we can say it's a transformer nodes, followed by the different nodes like Vi, Vi plus 1, so on up till Vn. The various power, that is the reactive power and the active power, which are flowing between the segments at the loads are being indicated as Pi and Pil. Similarly, for the reactive powers Qi and Ql. Resistance and reactance R and X are for the corresponding segment of the distribution, depending upon what kind of a line you are trying to take, whether you are trying to take an overhead line, whether you are trying to take an underground line. So this is typically a single line diagram of radial systems. With the help of this line, we have just drafted some important equations with the help of which we are in a position to explain how the power losses are going to take into consideration. Depending upon the first equation is just trying to show what are the losses in terms of active and reactive power which are occurring in the segments. The second equation is trying to show that with the help of the active power which is coming from the PV which is getting connected at one of the node, how the overall losses are likely to change. Initially, it is likely to get reduced, but more the penetration, it's quite possible the losses are going to go on the increasing side. This is the typical model which we have developed in the MATLAB, and with the help of this IEEE model, IEEE 13 bus model, we have done all our simulation and concluded on the observations which are available. This whole model is, the first model which I have shown now is without an SPV system. The second model I'm going to show with the SPV system. There are some nodes which are of more importance to us. The first node is this fag-end node, which is 646 node. And also we are going to concentrate on the node which is 611 node, which is also a fag-end node. And the third node is 675, which is the fag end node. So there are some things which are going to occur at this different nodes, which is of more interest to us, the fag end nodes and the source node. The source node is node number 632. So majority of the things of our observations were for the source nodes and the fag nodes. Also, this model is typically as per the IEEE description. So we have considered the balanced as well as the unbalanced condition. We have considered the single phase as well as the three phase load and the line segment. So if you just try to see, this is the single phase loads which we have considered, and these are the three phase loads which we have considered for analysis. This is the typical model which we have developed ourselves as per the IEEE standards without an SPV system. In the next slide, I have taken the with SPV system. So the solar voltaic generation is being integrated into systems. Both types of integration is being done, single phase as well as three phase. So wherever we were having the three phase lines, we have integrated the three phase load, three phase generators, and wherever we were having the single phase line and the load, we have integrated the single phase load into the circuits. For this typical model which we have developed, we have taken the values as per the conductor sizes and its typical values for the overhead as well as the underground nature. So depending upon the segment which has been described as IEEE, certain part is overhead, certain part is underground, and the resistance and inductance values which are been taken are as per the conductor standards values which are available in the data sheets of the different conductors. Presently, we have to go on with the low voltage system. So we have considered the AND conductor, which is a 50 square mm conductor, and GNAT conductor, which is a 25 square mm conductor. So these are the line parameters for the IEEE bus. Similarly, we have considered the bus parameters, wherein as per the IEEE standards, wherever there is a single phase load, a single phase load is considered. Wherever they have recommended a three phase load, a three phase balanced load is considered for the purpose of observations. We have gone with the MATLAB version of 2020, wherein we have worked with the Newton-Raphson's method for the load flow. These are the important observations which we would like to share with you. These are the different nodes which are present in the systems which I have indicated. The first column goes without an SPV system, and there is no SPV being integrated. What are the voltages values at the different nodes? To get this value, what we have done is we have increased the load in stages, and we have tried to identify when the voltage level is getting breached as per the IEEE standards. As per the IEEE standards, we are having the breaching level as plus 5% and minus 5%. So with the increase in load, where it is trying to breach the lower limit, that is the load condition which we have taken, and we have stopped with that load in the integration process. So if you just try to see the fag end nodes, which are the nodes which is 611, then your 646 and your 675. These are the nodes where we are seeing the breaching condition likely to occur very soon with a little bit more increase in the load. That is 0.95. That is 95% of the voltage levels. The next step, what we have done is that we have integrated the PV penetration, and we have increased the penetration in the percentage of 10%, and just try to see what are the voltage levels, effect on the voltage levels at different nodes. In the initial cases, we have observed that the SPV is trying to improve the node voltage by increasing the voltage levels. But as the integration is going on, increasing on a larger scale, we are observing that the voltages are getting, trying to breach the upper limits. And the source node is the first node which is getting breached on the earlier case. So if you just try to see with the defined conditions which we have developed the model, you'll find that for the node 61111, the breaching the source node 632, the breaching of condition is on the verge at 40%. And if you just try to increase the penetration more than 40%, the various nodes are getting affected, and it is going beyond the limits as per the IEEE standard. So this is the first effect which we have observed with the help of SPV integration on the voltage levels. The same thing is being shown in a graphical representation where we are trying to show the spread of the voltage levels with the different SPV penetration at the different nodes in the IEEE models. The second observation we had was related with the power factor. So Again, we have seen that as the SPV integration is going on increasing, what is the limit or what is occurring with the various power factor levels. If you just try to see that without SPV, we are having something which is a very good voltage levels. But as we go on increasing the penetration, you will find that the power factor is going on reducing. This is because the inverters are basically designed, or solar inverters are basically designed to generate active power. So if the load is trying to have a requirement of active as well as reactive, and since the reactive is remaining constant, it has not been given by the inverter, the power factor is been observed to go on deteriorating with the increasing the penetrations. No doubt in this case, the limit has not been exceeded, but in case of a heavily reactive loading condition, it's quite possible that the breaching of the condition can occur, and hence we need to take into this consideration when we are trying to design the maximum penetration levels. The same table is been shown in the form of a spread of the power factors at the different voltage node at the different nodes in a graphical manners. So depending upon the single phase or three phase loads, we have seen that the effect of power factor is different, and hence the graph is in this corresponding manner. The third study was related with the voltage harmonics and the current harmonics, and hence the total distortion which is present. Now, depending upon the non-linearity of the load and the increase in the penetration, it is observed that the harmonics are also increasing on the larger scales. As per IEEE standards, depending upon the voltage levels, we are having a set limits where beyond that, which we are not allowed to increase the voltage harmonics or the current harmonics or the total distortion of the harmonics. For the low voltage, when we try to talk about the IEEE's voltage, which is lesser than 1 kilovolts, the typical individual harmonics is somewhere around about 5%, and the overall harmonics limit is been set at 8%. Now, if you just try to see that in case of harmonics, when we say harmonics, we are trying to say related with the increase in the frequency. When we go to a higher frequency, and whenever we try to say we go with a higher frequency, automatically your reactive power is going on increasing. And since this reactive power demand is increasing in the load, the power factor and hence the harmonic distortion of the overall system is observed to be deteriorated. So if you just try to see the variation in the harmonics, almost from the condition when we have a pure grid to when we are having a larger penetration, it is almost having an increase of from 2 times to almost 10 times increase in the harmonics, depending upon the loading condition, the type of the loads which are present at the different nodes. Similar is the observation, the same observation I have shown in the form of a graphical representations with the different penetrations. Followed by this, again, I have shown the implementation or what is happening with the current harmonics also. In terms of current harmonic also, we are having a certain limits depending upon the individual harmonic, which can be between 3 and 7, 7 and 15, 15 and 23, 30 to 23 and 35, 35 to 50, and more than 50%. So again, the harmonic limits have been set by the IEEE standards, and 8% is for if you are having the ratio of I by IC to be lesser than 20. And depending upon the ratio of short circuit current and the load current, this is likely to be keep on changing. And the limits are also different for different current limits. Here I've tried to show you the percentage of harmonic changes which are occurring because depending upon the single phase load or the three phase load and the type of loads and the limits of harmonics which are present, we were able to observe the different harmonic increase in the percentage of harmonic with the increase in the SPV penetrations. Finally, I would like to conclude that with whatever models we have dealt with, we have observed that we were in a position to inject almost 40% of the, we are able to integrate 40% of the generation as compared to the load. If you are trying to do more than that, the factors which are getting affected. So the first factor is getting affected is the voltage levels. Followed by that, we are having an implication in the power factors and the harmonics. If we are able to control all these factors, the penetration level can go further higher, and that is what is the future part of my study. In this regard, we have gone with some development of some controllers, some power electronic devices, and we are trying to do with something with these STATCOMs, active filters and regulators, and a coordinated system is also planned. And with the help of that, we are trying to see that how we can go beyond 40% and try to take all this green energy into a network and try to move away from the fossil fuel or the traditional energies. Thank you for the attentions, and I we are open for the questions. Thank you, sir.
Thank you very much for your presentation.
Yes, sir. I have considered the transformer. That is the second part of my next paper, which I'm likely to present, wherein I have considered the transformer, its OLTC actions, and I've also considered the effect of the conductor size. So with the help of this also, we can increase the penetration level, but the most important factor which comes into consideration is the cost. So the cost and benefit analysis will help us to design what will be the optimum things which we should go in the infrastructure change. Setting of the loads.
Because you know which in
Presently, we have considered the static loads itself. So with the base fixed load, we have tried to see what are the observations. During the dynamic condition, the whole of the scenario is going to be something different. Yes. So we have done it, but due to the shortage of time and the paper limitations, I was not in a position to
that's
put everything in the paper.
recommendation
Yes, sir. Thank you, sir.
for two. Yeah.
Yes, sir.
Is a software from IFRI. That tool that is the variable software.
Thank you for your suggestion, sir. We'll surely implement it. Thank you, sir.
Okay. Anyway, any question?
Presently, the environmental degradation conditions are on a larger scale in Maharashtra and in India. Soiling is the worst case effect which we are observing in Maharashtra, because of which the life of the plant, which is expected to be 20-25 years, is not observed. Secondly, because of the climatic changes, a huge amount of change in radiance is also currently been observed, and that is also the second bottleneck on which peoples in India are trying to work out how to catch up with it, so that whatever is the forecasted energy that will be available, and there won't be a gap of demand supply when you are trying to cater this kind of an energy. We are basically having three kind of networks. We are having a central grid, we are having a state grid, and we also have a private grids. So depending upon which grid is being utilized by whom at any moment of time, we are having some three different dispatch center. We have something called as state dispatch center. Then we have something called as regional load dispatch center. Then we have a national level. And in addition to that, because of renewable energy, we are also having something called as renewable energy management centers. So with the help of this, the power flow in the whole country has been managed. Thank you.
So India. Thank you very much for your nice presentation. For the next paper is hybrid energy storage system to enhance renewable energy usage. Paper will present by right? Sorry. He's not PhD from Ksesat University.
Morning, everybody. My name is Thanwa Buller from Ksesat University. Today, I'm going to present the research about improving the stability of island microgrid based on hybrid energy storage management. The first thing is, I want to tell you is, this is not my work, because the author have business, so I am their replacement. You have a question, you can still ask me. I will try my best. Okay, let's start. This presentation divided in 5 parts. The first is introduction. The second is we discuss about hybrid energy storage system. The third is the proposed energy management method. And the fourth is the results. And the last one is conclusion. International Energy Agency, IEA, has reported that in 2050, the carbon dioxide emission will increase 130%, the oil consumption increased 70%, and the global temperature increased 6 Celsius degrees. To solve those problems, renewable energy sources have been implemented, such as hydroelectricity, solar energy, wind energy, and biomass energy. The problem is those energy sources have fluctuation. To solve this, you must use some energy storage system. But each energy storage system have their own response time and their lamp rate. The solution in this work we mix them together and use in hybrid mode or HESS hybrid energy storage system. This work we focus on two type of energy storage system. First is we discuss is the solid oxide fuel cell. Sorry. This energy storage system use hydrogen as a storage, and the hydrogen will feed into the fuel channel, and some electrochemical process happen, and we produce electricity from this cell, and the byproduct is we have water. This is slow cell discharge rate. And the next is the battery energy storage system, or BESS. This work we focus on lithium-ion battery. The lithium-ion battery most very popular today. We use the lithium battery ion in phone, tablets, laptop, or even an EV car. The advantage of the BESS is fast response time, high cycle lifetime, and high efficiency. Okay, this is a basic concept of frequency stability. If power supply and power demand is balanced, the frequency is constant around 50 Hz in Thailand, and the battery storage system not do anything. Okay, when the supply is higher and higher than the demand, the frequency rise more than 50 Hz. The HESS hybrid system has to discharge excess energy to regain the balance. In contrast, if the supply drop and demand has higher, the frequency drop below 50 Hz, and HESS will be discharged energy to compensate power mismatch. In this work, we use single area microgrid. The first is wind turbine. The second is PV system, and we have load of 1 megawatt. We have two energy storage system, or HESS, consists of BESS and SOFC. The condition we use differential frequency relay to take a condition, and the model is on Dixieland Power Factory. And the part one, we study about transient response. Okay, first the switch is normally closed at 0 second, and after at the 5 second, the switch open. Then at the 10 second, load increase of 50%. The results show that after switch open at T equal 5 second, and the the frequency slowly drop, but when the load increase to by 50%, the frequency drop higher, and the rate of change of frequency is minus 0.31 Hz for case without batteries or hybrid energy source system. And with the hybrid system, the frequency can maintain at 50 Hz. Okay. The next one, we simulate 3 states. We use data 24 hour of wind turbine and PV system. Also, the load also use to 24 hour too. Okay. Okay, the results show that when the load higher than the supply, the SOFC will charge the will supply the power to compensate the mismatch. Okay, and when the supply drop, when the oversupply, the BSS will charge the power to battery energy storage system. Okay, this is here is conclusion. We model Iceland microgrid with a single area 100% energy storage, renewable energy storage system, renewable energy sources. Okay, sorry. And ESS is characterized by the fast response time we use to respond in the short term, and SOFC is characterized by low self-discharge rate we use for the long term, like steady state simulation. The hybrid energy storage system can significantly improve the performance of renewable energy. This is the end of my presentation. Thank you for your attention.
Any question? Start from me. From my understanding, you have two types of storage. One is fast response, one is slow response, right? And you try to balance two types of battery, and this is called hybrid. And okay, usually the SOFC, okay, the emission is water, wind, but
Right, yes.
the hydrogen cost usually expensive. Question is, why do you choose the SOFC to generate the power first to the system?
I use SOFC because it's it can store energy larger and have energy density to supply in longer period than the energy source system. But it has a disadvantage to about low response time. So we used to mix them with the fast one like BESS.
To consider from the performance
Yes.
point of view, and you think that in the future the price is technology over. But okay, the idea is first priority is to use the green energy, right? But
Yes.
the problem is the response arm low. So for example, if the load is gradually increasing and generate power from it, but the load change which is higher than maybe some point, use battery. High discharge rate battery. That time maybe just something. Any question?
Oh.
Maybe go to the block diagram, right? Which?
Okay.
Yeah.
When the rate of change of frequency higher than 1.2 millihertz per second, okay.
1.2 millihertz per second. How did you obtain this?
Is used from hypothesis. Yes, from previous ways work.
To use as a simple rule.
It's
To
just
switch.
simple rule.
So what understanding rate of change higher than 1.2 millihertz per second. Third is fast response. Fast response. This value maybe
Yes, yes.
I see. More than this,
Thank you.
another question. wait.
Can please? This is we will demonstrate the concept. I'm not sure I understand the question, but in the future work we use full model of transmission line and distribution line. Oh, you mean load profile? Load profile. Oh, sorry. I think
It's just other this.
yes. Thank you. Thank you.
Thank you very much for your presentation. Let's move to the last paper of this session, which is optimum peer-to-peer energy trading, applying blockchain to island microgrid considering V2G. This paper will present by sorry, no biography. Please introduce yourself. Gladly University.
Hello. Good morning, ladies and gentlemen. My name is Bulan Yusapan. I'm a master degree student from Culinary University of Technology. Here I would like to present my paper, the topic of chain-based optimal peer-to-peer energy trading modeling, considering V2G in a isolated microgrid. Outline of my presentation are includes as follow. First, introduction. Second, objective. Third, methodology. Fourth, problem formulation. Fifth, liaison discussion. And finally, conclusion. So my introduction is, in this work, we assign islandless microgrid to be a smart microgrid. It is comprised of battery energy storage system, solar power plant, and distributed generation. And in this system, directive vehicle also include in the microgrid to be grid vehicle to grid or V2G concept. This islanded microgrid has energy management system as power consumption, cost operation optimization from microgrid. In this case, in this case of energy insufficiency, prosumer can consume the power from other prosumer or selling the power to other consumer or the primary power grid. The motivation of this work is from a combination with using energy trading between islanders microgrid for corresponding electricity demand. The objective function of this study to determine the optimal operation cost of islander microgrid in a daily operation, simulating energy transaction when including V2G and energy storage device, and using blockchain to create safety and build confidence for buyer and seller with complex inscription in peer-to-peer energy trading. Methodology. Peer-to-peer energy trading in the transaction between microgrid, peer-to-peer energy trading is addressed as energy trading between an end user. A significant highlight of prosumer and consumer energy transaction. This means that each end user can be both producer and consumer. Alternatively, in the other word, the microgrid consists of the seller and buyer at the same time. Blockchain in transaction. P2P energy trading allows both seller and buyer to set the trading price independently. Applying the blockchain in P2P energy trading is inspired by the secure of blockchain in cryptocurrency trading to build trust in a seller and buyer energy trading market in a microgrid. Indeed, research using blockchain into be a secure base in a transaction simulate. Identification of seller and buyer. In this study use a random sense Twitter pseudo. Random is number generate model. Such a model is used to predict the power demand of load and generate a time slot. We define upper bound and lower bound according to equation 11 and equation 12. Also, the model has random values corresponding with maximum renewable energy load in the system. Note that an energy surplus is in equation 14 and energy deficit is indicated in equation 15. Price adjustment and contract mechanisms. The trading market will be considered in each match during the period time as follow in the first. If seller price is less than a buyer price, they will automatic indicate purchase contract. Second, if seller price is more than buyer price, the buyer price will choose another option. And the third is if buyer does not have a matching contract in the first round, the seller must reduce the seller price according to equation 16. If the buyer price shall increase the trading price according to the equation 17. Vehicle to grid or VTG. This study assumed that EV include each sub-microgrid. The VTG is a vehicle action as an energy storage device and supply of energy to the grid. Two types of EV actions that are used in this simulation is a charging mode and discharging mode. Objective function and all constants are followed as equation 1. The constant where is the power of distributed generator, power of battery system, and net power are equal to net load, which means the power balance in equation 2. Boundary of dispatch generator is checked by state variable in equation 3. And equation 4, variable indicated the status of on and off of the generator. And equation 5 show the operation should not be on and off in the same time. And the charge and discharge status of energy storage system are slot by also set by equation 6 and equation 7. Why the charge and discharge should not be operated at the same time is equation 8. And equation 9 presents the state of charge or SOC with energy charge and discharge effect to be assessed at the time. Boundary of SOC is limited by equation 10. It's all in this question. Figure 1, the power net of 5 microgrid as hourly in the one day. As shown in the figure 1, all some microgrid can divide into two groups. Group A is positive power net and group B is negative power net. For the example, in a hourly 7, microgrid 1 and microgrid 2 are group A that consume the energy and are ready to buy. buying the submicrokit 3 and 4 and 5 are group B that have a net power over demand and they are preparing to sell. The figure 2, optimal operation cost in the daily operation of the microkit must determined by the augmentation constraint. The figure 2, microkit 1 can consume energy from microkit 4 with a lowest price from a consumer viewpoint. While on viewpoint of prosumer, microkit 1 can sell energy to microkit 4 with a highest price but not higher than another microkit. Table 3 trading result in RE5 and RE12. From trading result that is the final price has been agreed upon by both parties represented in table 3. For example, microkit 2 as a prosumer selling 7.57 kilowatt of the power at $0.16147 per kilowatt. So the microkit 1 and microkit 2 will receive a total selling price of $1.2223. Figure 3, transaction data in blockchain. To create safety and build confidence for buyer and seller with complex encryption. Peer-to-peer energy trading must have high security in transaction because such trading is still an intermediary system. So that simulation applying the blockchain and peer-to-peer energy trading, a blockchain is store the data in a transaction data storage history, trading history and personal data in hash format, as shown in the figure 3. Conclusion. Peer-to-peer energy trading is a promised model for small energy trading to participate in the market. When considered V2G in peer-to-peer energy trading, V2G contribute to more significant rate of energy trading. According to the simulation, the applying blockchain in a energy trade is considered is good skill measure. That being me today, and thank you for your attention. If you have any question, please don't hesitate to ask.
Okay, from my understanding, you are focusing on the blockchain technology, right?
Yes,
On
it's,
this,
blockchain is my base on the system.
so can you go to the site? Objective you have. Which parameter you want to?
in my work, I want to optimize and minimize operation.
That's objective, but which parameter?
Which at the power distributed generation at the PT ETT. Did you see?
Want to no
Sorry.
want to finding this our set point. Thing.
Yes,
You have
finding
different
our-
type of source and load, right? In order to obtain, you must vary some. What is the variable you want to optimize?
The variable that I optimize.
Yeah, and I will ask you next question: how many variables you want to optimize? Usually we write, this equation into 3 parts. First, parameters. and objective. Also, you talk about V2G, right? V2G, which really, in order to discharge the power from the car, starter put all the SOC, existing SOC, price, E-grade, battery lifetime, boost V2G. Possible SOC is possible to discharge the power. 50%, okay. 80%. We considered
My work is nothing consider that with I will apply in my future work.
Anyway, we have certificate. If this certificate one by one.